imagine that we are sitting, living on the surface of one of these rubber balls, which is inflating. And you are at a point there. So you see your space is inflating. So you are not living inside in the gas. You are living on the surface. And that is a much better. And that tells you also that every place in this universe is equal. There is not a center. There is not, because every place in a perfectly spherical balloon is equal. So everybody in the universe would observe the same type of phenomena. So this thing is expanding. So one way in which we can study the past, because we are all interested in what is happening there at the beginning, and the religions are really interested in what happened before that beginning. That is a different story.
We talk about that later.
And one way is just to look at distant object, because since, as we were saying, the information moves at a finite speed, if you look at a thing which is very distant, as a matter of fact, the more distant this object is, the more you are looking in the past, because the information which arrives now is the thing which started there and years ago, and so on. And now we are capable of looking really very, very, very... And so the more distant you look with this beautiful telescope you put in the space, the more you are closer to the origin of the time. But there is a limit to that, because the universe, for some time, it was so hot and so dense that information could not come out. So the information was produced and reabsorbed because it was too dense. So you can arrive up to a point which is about 300,000 years after the Big Bang, which, I mean, looks already good enough because it is 13.7 billion years. But we are more ambitious than that. And so we did, Goethe was saying the Klein Mensch, jeder Quark. Goethe was the first person who used the word pork, quark, because pork is a soft cheese in Germany. Means a mud, things like that. The cheese is a bit better than mud, but it's in other Quark begrabter seine Nase. So what we did is just to try just to recreate.
Protons exist of quarks, so we have to explain it a little bit.
We were trying just to recreate the condition which were existing at the universe locally in a small place for a tiny amount of time, 10 to the minus 30 seconds, in a very tiny amount of space, a volume so small that I don't even tell you the number. So it's 10 to the minus 40 cubic centimeter. But in this way, we can go very close to the origin, to the zero, to the time in which time started. With the LHC now, we are getting to 1/10 of a billionth of a second after the Big Bang. So
now.
Huh? So that's why we are all excited.
You can imagine.
And essentially, there are two ways. Imagine this is a special type of ruler. Every tick there is a factor 10. So this end is the size of the universe now. And this end over there is the size of the string, which is the smallest thing theorists can tell now. And we are more or less, we are smart. We have chosen the scale in such a way that the band is midway there. So, and essentially, we can look at things like that, or we can look with the telescope, or we can look just going down. And in order just to observe things closer, we need just to have more and more powerful microscope. And an accelerator is essentially a bigger microscope through a mechanism which I will tell you. In the beginning of last century, quantum mechanics has told us that particle and waves are two aspects, have a duality, are two aspects of the same thing. So, connected to a particle, there is a wave function, and the highest is the energy of this particle, the shorter is the wavelength. If you want just to see, we cannot look at things which are too small with a microscope, with an optical microscope, because if you want just to look at two things at a certain distance, at these two things, and separate them, you need just to use something which the mechanism of sight is that there is light, photons are impinging in these two objects, they bounce in my eye, and since their wavelength of each single is much smaller than this distance, I can separate this object from this object. The more I bring this object together, the more they becomes compatible with this wave which I soak these two objects. Then at some point, the information which comes back confuses this object with this object because the wavelength is bigger than this distance. The only way for me is just to make a smaller wavelength. And that is exactly what accelerators do. Accelerators are making smaller wavelength which allow us just to explore nature up to a scale to 10 to the minus 18 centimeter, which is a very small number with this energy. With more energy you go much higher.
Yeah.
I can stop here.
Okay, well, this is very important, of course. But we saw some balls,
Yes,
but you don't. That's a false model, of course.
absolutely.
But so, don't believe the drawing. But what is in effect a good model to visualize a quark, for instance?
Oh, a quark. A quark is a beautiful thing in the sense that they exist, but they cannot be seen.
That's nice.
No, they can be seen. They cannot be seen living in a free
Separately. Yeah.
separately. Because, and we have understood also why, because otherwise looked like an ad hoc explanation. Quarks are constituents of the matter. Now we know that we can create all the matter, the normal matter, the one which is done ourselves, the stars, even the exotic matter of the beginning of the universe is 4%, with only 6 quarks. We are made out of these 6 quarks, we are made out of 2. All the normal world and the universe at this level of temperatures and now is made by only 2 of these quarks. I will just go back here.
Yeah.
No, it's just go back. And these quarks are called, have a conventional name. They're called up and down, charm, strange, top and bottom. Or since bottom has more than one meaning, we say truth and beauty. Let's say so. Okay, we know that we can create all what is around us essentially by these 6 quark and 6 sort of other things which are called leptons, which are. One of them is very popular, is the electron. Another is less popular, but also very abundant in every moment. For instance, now we are crossed by cosmic rays coming from the universe, and in there are a lot of muons. Muons are electrons which have grown very heavy, but they are totally similar. They have all the same property of an electron. The same charge, the only thing they have a mass which is 200 times higher. And then there is even a bigger relative which is called the tau lepton, which is again looks like an electron, but is 3,000 times heavier than that. And associated to each one of these leptons there is a flavor of neutrino. A neutrino electron, a neutrino muon, a neutrino